Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So you recall that during the first two lectures we talked about decentralized systems, and particularly we talked quite a bit about DHT or KBR-based structured overlay distributed systems or decentralized systems. And in particular in the last lecture we talked a lot about the difficulties of implementing these systems in the presence in a deployment in the wild, where you have to expect that some of the nodes that are participating in your system are malicious, when you have to be prepared for massive failures, in some cases massive correlated failures, and you're still trying to maintain some level of consistency, reliability, and quality of service. And we talked in particular a little bit about the difficulty of protecting such a system from malicious participants, and you saw how much complexity it actually takes to just protect the key-based routing primitive, the basic underlying primitive that allows you to look up a key and find the associated node that is responsible for that key. And I sort of mentioned in passing that that's not the end of it, right? If you're implementing an application, you also have to worry about cryptographic techniques to protect your data. You have to perhaps worry about denial of service attacks. You have to come up with some strategy of controlling your node population, defending against Sybil attacks, and so on. So it all becomes quite daunting. And in fact, we had a few years ago, towards the end of our own activities in this realm, done a little project to try to see, what the complexity would be of actually putting together an application that solves all these problems and provides a useful application under these sort of pessimal assumptions. And what we did is we built a little email system, a completely decentralized email system called ePost. That our goal was to make it robust enough that we would ourselves feel comfortable using it for our daily email, which means you'd be concerned about availability because you want to read your email, and you'd also want to have a reasonable confidence that it's not losing data because nobody wants to lose their email. It's what we did, and it was quite an engineering effort over a period of, I think, 2.5 years. And we had to do many of these problems, and towards the end of that experience, we sort of thought, well, this was really complicated, and we wished there was a more general, better way of dealing with a lot of these issues related to malicious participants. Now, one way that you already heard about it, one other approach that you already heard about would be to use Byzantine fault tolerance. Use Byzantine state machine replication and simply say every node in the DHT is now being replicated, say 4 times. Use a replicated state machine, and now you can tolerate one of these nodes in each of the groups of 4 being malicious, and it'll still work, no problem. And indeed, that's one of those very general approaches. Right? You don't need to solve these individual problems and worry about these individual attacks because you have a very broad, general blanket mechanism. But the cost, of course, is that now you need to do this consensus protocol on every one of your actions that you perform, more or less. And the other issue is you have this fault bound. Say you replicate 4 times, so you can tolerate 1 faulty node per group. The issue is if you have a very large system, then even if you only expect a very small fraction of the nodes to be malicious at any given time, there's still sort of a non-trivial probability that it just so happens statistically that somewhere in your system, one of those groups of 4 will have more than 1 faulty participants, right? And then, you're stuck again. Of course, you can go to 7 replicas, right? And then you can tolerate 2, but that just changes the probabilities a little bit. You're not getting away from the fundamental underlying problem that in a large system, there's some non-trivial probability that your fault bound will not be satisfied somewhere in the system. So anyway, long story short, we started to think about alternatives at the time, which got us onto this track of thinking about accountability, which is also a very general approach, but it sort of says, well, in practice, particularly in the decentralized system, nodes fail anyway. So if there is an unmasked failure every now and then, perhaps that's not so difficult, that's not such a big problem. If we can detect it and then make sure that the node that has committed this fault is removed from the system, so it can't do whatever it's doing on a permanent basis. Okay, so let's get into this. So let me try to first motivate this a little bit more generally. So we're interested in faults and misbehavior, which of course are not unique to just peer-to-peer or cooperative systems. They appear in virtually all large-scale systems simply because the complexity of the hardware and software is such that you have a certain number and rate of faults. So this affects essentially all internet-scale systems. You're particularly also worried about non-trivial failures in systems with multiple administrative domains, where the trust and control of the system are decentralized, because there you run into situations where, intentionally or not, there are deviations, right? Like one party thinks the other party is doing something, but they're actually not, because they're operating on a different set of assumptions. It's even worse if you are in a system where actors have explicitly competing interests, which increasingly also happens in the internet and the World Wide Web. You have competing businesses. So that means they inherently have no incentive to operate with full transparency, right? They want to keep their own proprietary information to themselves. They don't want to give you full information about how they're operating their business, which again is a problem if if something is not working right? You have the difficulty of finding out what's actually happening, who's causing the problem. And finally, and we're back to these peer-to-peer systems, if you have systems that actually depend on cooperation, either cooperation of the sort where you expect people to contribute resources, or cooperation of the sort where you're expecting users to give constructive input, or just follow the rules, right? It's like be good citizens. Then you have to be prepared with the possibility that some of them won't do that, right? And that disrupts the system in some shape or form. So again, we're focusing here in this line of work, not on masking or preventing these kinds of faults and misbehavior, but on detecting them reliably. So what makes it so difficult to do that in general in a distributed system? Well, first of all, there's a problem of detecting the fault, right? Often you are observing the system from the perspective of one node, and all that the fault manifests itself with, it may be an incorrect message that you receive, okay? Where it's often not obvious to even realize that this message is incorrect, meaning in a correct execution, you should not have received this particular message at that particular time. But even if you are somehow able to realize that this message is incorrect, now you sort of have to trace it back, potentially through a causal chain that caused this message to arrive at your node, back to the node that ultimately was actually responsible for it, right? So the little one with the devil here. This is the actual culprit. This node set off a chain of events that ultimately led you to get an incorrect message. Now, even if you were to identify this node now, which is non-trivial because you may not have complete visibility into the system, right? It's maybe a federated large-scale system where you're not controlling all the different parts. So even if you are somehow, have good reason to suspect that this node is responsible, you still have to convince the responsible admin for that node that they are, in fact, that they have a problem with one of their nodes. And they may be reluctant to believe you, right? Because it's always easier for us to assume that the problem is somewhere else, particularly if we ourselves are not observing any problem. Okay, so the third problem is, once you have suspicion that you've identified the root of the problem, how can you actually prove this to a third party? So let's look at some of the techniques. So first of all, let's take a step back and learn a little bit from the offline world. So if you think about it, the way we are dealing with faults and misbehavior in human society actually rarely relies on fault tolerance. Okay, so there's not 4 copies of Peter up here, and before I utter a word, these other 3 guys check whether I'm talking nonsense, and if I do, they'll gag me. That's not how it works. In fact, we're relying on accountability, right? So if I talk too much garbage here, then the organizers of this conference will simply not invite me next time. And they will tell their colleagues, right? So that everyone else in the community will also know Peter just talks garbage, don't invite him for a talk. It's based on accountability, right? You sort of assume that people are acting in good faith, and if they don't, you make sure that next time you take the appropriate actions. Now, looking specifically at the example of a bank, what they actually do is they have an elaborate system of accountability. So when you go to the bank and you deposit some money, they give you a signed receipt, which you can use as proof that you actually deposited the money at the bank. Okay. They are also maintaining a tamper-evident record of all the transactions they perform, using a technique called double-entry bookkeeping, which is designed to make sure that a single agent cannot unilaterally change that record without causing a discrepancy. Okay. So you want to make sure that there's a balance in all the bookkeeping so that one person cannot simply cook the books without causing discrepancies. And finally, they have a system of inspections where periodically the internal audit department of the bank, or maybe even law enforcement in case of a crime or a suspected crime, or the tax authorities can come in, inspect these tamper-evident records and see what happened, did anything go wrong, and if so, who's responsible. So they keep this record, and this record can, in the traditional offline version of accountability, be used to manually detect faults, identify who's responsible, and then use that evidence, right, those books, to go to court and use it as a proof to accuse someone. Now, the question we're asking here is this concept, is that concept in fact useful in distributed systems or in computer systems in general? And if so, then is it practical? So let's be a little bit more specific about what accountability means in the context of computer systems, at least in the sense that I'm talking about here. It consists here also, just like in the banking example, of a tamper-evident log, a tamper-evident record, in this case not of a set of transactions in the financial world, but of a distributed computation. Okay? So some distributed computation is running, you're keeping a record which has this property that if anyone tried to unilaterally tamper with it, it would cause an inconsistency that you could detect. Okay? And that's why it's tamper-evident. Plus, you have a system that allows you to reliably detect faults based on this record. Okay? In this particular case here, that fault detection should not be manual as it is in the bank books or in conventional bookkeeping. That would simply be impractical, right? Because logs of computations are so verbose that nobody would normally bother to inspect them, unless maybe in cases of severe crime or severe accidents, okay, where this is imaginable. So the next question you might ask is it actually useful in the context of information systems? And the answer is clearly no if you think about faults that have severe and irrecoverable consequences. Right? The most obvious example is if we're talking about embedded systems, right, where you have a computer system that effectively controls physical equipment, physical actions, like controlling the avionics in your airplane. You don't want to have accountability, right? Except maybe as an additional mechanism, in addition to fault tolerance. Right? But the primary mechanism you want to have is fault tolerance to prevent this airplane from crashing. But of course, fortunately, there's an extensive literature on fault tolerance, and that's all good. But I would contend that accountability is in fact useful if you focus on systems that either provide, by definition, a best effort service. Right? Any system that is designed to provide a best effort service implies that sometimes it can fail, and that's okay. Okay? Apparently, it doesn't have such severe consequences that is completely intolerable. Yet, you would still want to know when something goes wrong, and you would want to know who's responsible so that you can maintain good quality of service. It's also, I think, useful whenever you have a system that depends on user cooperation, because it isn't really practical to apply fault tolerance to users. Right? You'll simply have to expect that they might sometimes misbehave. I would contend it's also useful for fault-tolerant systems that are designed on the assumption that nodes only crash. because when and if that assumption is violated, meaning a node actually fails in a way different from a crash failure, it actually actively misbehaves, you have no way of masking that fault, but at least you have a way of reliably detecting it. And then, of course, there's a class of systems that fail rarely enough, and the consequences of failure are, in a financial sense, tractable enough that you can rely on insurance. Okay, so you just say, I know the system can fail sometimes, I'll buy insurance for it. But in those cases, you really also want to have accountability as a way of knowing when something went wrong, who's responsible, because that's also what the insurance company would want to know before they settle the claim, and they will also need that for their own risk calculations. Okay, so we want to look for techniques that can reliably detect faults, and if we have that, the promise also is that will actually provide incentives for participating, computers, users, organizations to avoid faults, right? Because this is a sort of a basic psychological effect. If you know you're being watched, you make an extra effort, right, to avoid misbehavior. And that in turn can build trust, right, in a forward-looking way. Like if you meet a person who you don't know, you're more inclined to trust them if you know that you actually have a way of watching what they're doing. At the same time, in a more backward-looking manner, if someone comes to you who you don't know, but you know that there's been a system of accountability in place and you can check their record and you know that they're behaving well over a period of time, you're also more inclined to trust them, right? It's a way of building reputation. Let me close this motivational part with a quote from Butler Lamson, who wrote this in a paper he wrote back in 2000. And I'll let you just read that little quote. Okay, so let's get a little bit more specific. So in particular, I want to ask the question, what can we actually expect from such an accountability mechanism? So let's define a fault here loosely as an instance of a node that deviates from the expected behavior, where the expected behavior is presumed here to be specified either by a formal specification, if you have one, or, more practical, by the behavior of some reference implementation of that system that you trust to be correct or you assume to be correct. Okay? Now, again, our goal then is that based on this definition of node misbehavior, to detect such faults, to identify the faulty node, and to hopefully produce evidence that you can use to convince a third party that a fault has occurred or has not occurred. Because sometimes accountability is also used to prove innocence, right? Someone accuses you and you say, look at my records, actually I did everything wrong, you're wrong. So let's ask the question, can we build a system that has this informally stated guarantee that whenever a node is faulty, so it exhibits an instance of misbehavior, the system generates a proof of misbehavior against that node. So it turns out it's going to be impossible to get that for a number of reasons. So first of all, at least in a practical sense, impossible. So let's first of all look at this particular problem here. Misbehavior in any way might include a simple problem where the internal memory of a particular, the internal state of a given node has changed by 1 bit, right? That's a single bit flip. So under this definition I just gave, we would have to immediately be able to prove, to generate a proof of misbehavior. But that would require that we have some kind of a trusted probe that constantly watches the internal memory content of a node, realizes there's a bit flip, and produces a proof. That's not really practical, right? We don't have such trusted probes, and in particular, those trusted probes would themselves have to be somehow reliable, right, and maybe subject to accountability. So therefore, let's settle for a somewhat more modest goal. Yes?
I would imagine that the accountability you're mostly interested in the external behavior of the component, not really care about what the internal state is.
Yes. Right. In fact, if you see what the next point is making is we're actually focusing on observable faults. I was trying to make the point here that, what are the fundamental limits of what we can do? Of course, you're right. It doesn't seem particularly relevant whether there's a bit flip in the internal node, except that maybe it may sometimes delay when you can detect the fault, right? Because you have to wait until that internal bit flip actually has some observable consequences. So anyway, we'll focus on observable faults, namely faults that affect the correct node, right? So the idea here is, as soon as this bit flip actually causes this message to send a message or fail to send a message to a correct node, so that the correct node can observe something is not the way it should be, right? At that point, we have a manifestation of a fault that we are interested in here, that we want to capture with accountability. Okay, and the nice thing, of course, is we can do that without requiring trusted components. We can simply rely on the observations of the correct nodes in the system to tell us when something has gone wrong. Okay.
Are correct nodes also assumed to be clients? Is the client can client or users be correct?
Yes, so we're going to assume throughout here that the system is completely symmetric. Okay. So the next thing is, can we always get a proof? So the question is, once we have one of those observable misbehaviors, can we always get a proof of misbehavior? And unfortunately, there's more bad news. Even that we can't get, okay? Because we have situations such as this one. So A claims that A has sent the message X, but B says, I never received X, okay? So there are three possible explanations for this scenario, right? It's possible that A is lying. It says, I sent X, but it never did. It's also possible that B has received X but refuses to acknowledge that fact. Okay? It's lying. Or it's possible that X was actually delayed or lost by the network. So neither A or B are lying. It's just that the network has not delivered the message. Okay? So in this particular case, it's impossible to produce a proof of misbehavior. Well, what we can do is, and again, I'm sort of working on weakening, our expectations, is to instead try to obtain something I'll call here verifiable evidence, which is either a proof of misbehavior if you can get one, right? Namely, someone actually acts, performs a commission fault. They perform an act that is wrong. Or in the case like this one, where you're not quite sure, you can try to produce a challenge that a potential suspected faulty node could not answer. So what would that be in this case? In this particular case, A itself or X itself would be the challenge. Okay? So imagine that X simply says, here is the message X that I claim to have sent to B. Okay? I'm going to sign that message cryptographically so that I cannot later on go back from that statement. And I simply tell all the other nodes in the system that are interested in the performance of B that I suspect B to be faulty because I cannot get an answer from B. Okay? So what the other nodes will do is they will simply take that message and they try to deliver it to B. Okay? If the reason for the observed problem was in fact just a network failure, then B should eventually be able to acknowledge that message, and then everything is fine. Okay? But while B has not acknowledged the message, we're simply going to assume that it is suspected, which is not a proof of misbehavior, but it tells us that there's something, either there's a network problem or B is in fact faulty. And an application can now interpret this in the appropriate way. For instance, one effective way would be to say, while B is in the suspected state, we're not going to talk to it. We'll just shun it. Okay? That might in general be a good idea because it prevents faulty nodes from selectively refusing certain messages. Okay? There's a common technique where whenever people offer you a favor, you answer immediately, but when someone asks you to do some work, right, you pretend like you didn't hear it. That's the kind of thing you want B not to be able to do. Right? And it could do that if you just always said, sorry, I didn't get X. Okay, so there's actually a couple of more things we can't do, but let me cut it short at this point and just say, here is a revised problem statement that we'll see is actually doable. And that is, again, informally stated, whenever a fault is observed by a correct node. So notice, again, we're focusing on observable faults by correct nodes. The system eventually generates verifiable evidence against a faulty node. So the verifiable evidence you see has been replaced with the proof of misbehavior, right? Because sometimes you can't get it. I also inserted the word eventually. That's just because, in an asynchronous network, It's hard to talk about hard time bounds. And you may also note that I slipped in an A here instead of the expected the faulty node. Okay, that's because there can also be coalitions of faulty nodes, and as it will turn out, in those cases, when a coalition, collectively commits an instance of misbehavior, we can only guarantee that one of those guys will be flagged as having misbehaved, but we can't control which one. In fact, the coalition can't decide which one they want to expose. But that's still okay, I would argue, because it means for every instance of a misbehavior, right, every single false message that's being received, you're going to knock off one of those guys from that coalition. So I would argue this is still useful, even this weakened definition. And of course, most importantly, it's actually practical. So an implementation of this of this general concept, one of them is called peer review. You can view it as a library that you can link against an existing distributed application, and thereby make it accountable. Lend it this property that it can maintain a tamper-evident log of what it's doing, and then it has a way of detecting faults or misbehaviors. In fact, the particular way in which this system detects faults or misbehavior is via state machine replay. Okay? So you remember you have this trusted reference implementation that you assume to be correct, and the way you decide whether some other node that you want to audit has performed correctly is to see whether that execution that it has recorded would have resulted in the same output when replayed against this trusted reference implementation that you have. Okay? In other words, suppose my own implementation is the one I trust. I basically check whether another node that I want to audit would have performed exactly the same actions given exactly the same state. Okay? Now, this is only one way of doing fault detection. You could do it differently, but this is the one I'll be talking about here. So to make this work, you have to, of course, rely on some assumptions. One is that you can model the node actions as deterministic state machines. That's a fairly common assumption that, for instance, you also make when you use replicated state machine protocols. Okay? There's an assumption that every node that wants to audit other nodes has access to a trusted reference implementation. They don't necessarily have to agree on which one it is. It's sufficient for one node to say, I believe this implementation, and that's the one that's my gold standard. You have to assume that correct nodes can eventually communicate. That, again, that's one of those weak synchrony assumptions that you also have to make in consensus protocols. And we assume that nodes have unique signing keys. So let's look, let's first take a very high-level view of how this system works. Here's a set of nodes. I arranged them in a ring, but actually the topology doesn't really matter here at all. Okay, so this has very little to do with DHTs, except that it will also work for completely decentralized systems. When a node A wants to send a message to a node B, A first adds this message to its own tamper-evident log. We'll talk later about what exactly actually makes it tamper-evident. For now, you can think that it's some local log that the node keeps. It sends the message, and B then adds that message into its own log, and that's it. Okay. The other thing that happens is that each node has an assigned set of witnesses, and the job of those witnesses is to periodically fetch the log from the node they're witnessing, okay, and then apply some kind of a test. I've already mentioned state machine replay, and based on that, if A turns out to be malicious, meaning it has performed an incorrect action somewhere, these witnesses are bound to find out if they themselves are correct. Okay, and furthermore, they can produce from the logs some compact evidence that they can then distribute to any other node who's interested in the status of node A, so that they can, in fact, themselves verify whether A is correct or not. Okay, so at this point, of course, you for sure have many questions. because it's not obvious why this would work. So let me try to address perhaps some of the concerns you have. First of all, how do we make sure that we can detect tampering, right? Because one of the easiest attacks a node could perform, it performs some misbehavior, like it sends an incorrect message, but then it records in its log, the correct action. So the way we do this is, first of all, whenever a node sends a message, it's supposed to sign that message cryptographically. Whenever a node receives a message, it's supposed to answer with an acknowledgement that's also signed. Okay. Furthermore, so notice that this already makes sure that nodes cannot lie about which messages they have sent, and nodes cannot later on lie about which messages they have received, right? Because they signed a statement to that effect. The second thing we do is those local logs that each node maintains actually are structured as a hash chain. Okay, so each successive entry in that chain contains the hash value of the previous entry, which means that the top level hash value is actually unique to the entire chain in the appropriate sequence. Okay, and whenever any node signs a message, whether it's a message or an acknowledgement, it includes the top level hash value of its current log in that message, which has the effect that every time you send a message, you actually commit to your entire history at that point. Okay? And you can already see that this makes it really difficult later on for a node to tamper with its log and not be detected, right? Because when I change the contents of my log or I put something in that shouldn't be there, I'm committing to it, right? Because I'm including that hash value in the signature that I sent. Okay, so the next question you might have is, what if a node actually just simply omits certain messages, right? So whenever I send a bad message, I simply don't add it to my log. So what's happening here is, remember, periodically, when this is node A, A's witnesses will inspect the log of A, covering all the actions that it has performed since it was last audited. So as part of a side effect of that, A's witnesses will look for the kinds of signed messages that they find in that log. Okay? And whenever they send, they see a message or an acknowledgement signed by some other node B over here, they will collect those signed messages. Actually, not the complete messages, only the authenticators. And they'll periodically send all those authenticators that they have collected about another node B to B's witnesses. Okay? And this is the way that B will eventually, because everyone's witnesses does this, B's witnesses will eventually find out about all the messages that A has ever signed. Okay? Sorry, that B has ever signed. Okay? So whenever I'm sending a message and sending it to anyone, right, I know that evidence of that message or that acknowledgement is eventually going to reach my witnesses. Okay? And now you can see the discrepancy. When the witnesses later audit my log and I have omitted the message, they will see the discrepancy. And they immediately will have a proof of misbehavior, right? Because they have something signed by me that is not in my log. Okay, so the next thing a clever node could do is to say, let me actually branch or fork my log or keep multiple copies of my log, basically splitting the universe in two parts. Okay? So one way you could use this, for instance, say you're implementing some kind of a file service or a DHT. So in one version of your history, you would say, somebody read some object Z, you say, okay, then some other node asked you to create an object X, and you said okay. Okay. But when someone else from another view asks you later on to read X, you say not found. Okay. Now notice that both of those histories individually, like if you read it this way or this way, they're plausible. Okay. But of course, both versions of history cannot exist at the same time, cannot be true at the same time. So we need to somehow figure out, or we need to make sure that nodes cannot play this game. And the way this is again done is that when the witnesses check a node's log, they will also insist that there's in fact a linear chain of hashes between any two entries in that log. Okay? So if they do that, and the node has in fact at some point split its log or forked its log, then there must exist pairs of authenticators for instance, this one and this one, that are not in fact connected by a linear sequential chain of hash values, right? And this is how a witness detects that a node has branched its log. And if it does that, of course, again, that's a proof of misbehavior. Okay, so yes. Yes.
So what in the previous slide, what happens is that the node would now give two different logs to its verifier. The friends that are auditing it, the peers that are auditing it, it would give one log to one peer and another log to another peer.
Right.
And they compare their logs and see whether I'm telling different things to different people.
Right. So what's actually going to happen is, remember, you have multiple witnesses, and those witnesses will, because of this other mechanism of collecting authenticators, they will eventually find out about all the messages that I ever signed. I have no control over that, right? So if I have only one correct witness, that witness will learn about all my authenticators, and if I deliver to it just one version of my log, inevitably some of those authenticators will be missing from it. You had a more general question.
One other question is that, so to me it seems like, initially I was thinking that this kind of methodology plays a lot of constraint on the way the systems are designed. In the sense that initially I thought that before I write, I have to actually log, and I have to have an atomic operation where I set. But some of these things seem like you are more robust to, or, systems being designed without following, perhaps all these rules. But
Right.
one thing I am not sure about is determinism, in the sense that, if a node executes something, I might just do a malloc, and I don't know what's that. I mean, there may be several sources of non-determinism in the system, and I'm not quite sure how you can reflect. And I don't
Right. So let me actually defer the question slightly, because I think it'll become clear. There's two ways of doing it. First of all, you can do the same sort of things that you do in replicated state machines, right? You basically extract sources of non-determinism, like random number generator seeds or external measurements you take. You just make them part of the log, okay? Thereby basically making them quasi-deterministic. The other interesting thing is, well, I'm getting too far ahead of myself, but it turns out you can actually take an arbitrary system image and just stick it into a virtual machine and apply this technique without changing a bit about it. But let me defer the question, and if you still have a doubt at the end, let's discuss it. Okay, so what I just explained to you is not comprehensive. It's certainly not a proof, but at this point, I'll ask you to trust me that, in fact, you can show at this point that the collection of these mechanisms that are in place here are sufficient to show that this log is, in fact, tamper evident. Meaning, it either, after you performed a distributed computation with a set of nodes, and then you collect all those logs, there's a test you can apply that'll either tell you, yes, this is in fact an accurate record of the computation that happened. Everything is consistent. Every message is accounted for in the right order. Or you can pinpoint a node that has in fact deviated, right? That has somehow cooked its books. Now, of course, at this point, we only know, yes? Yes, sorry, I'm being a little bit imprecise here. The precise condition actually is you need to have at least one correct witness. Okay. And the pinpointing the faulty node is also subject to this thing I said earlier. If you have a coalition of faulty nodes, you will detect one of them. But I'll be a little bit more precise in just a second. So anyway, notice at this point we just have a tamper-evident log, right? And if it all checks out, we know that everyone has recorded their actions accurately. But we still don't know whether everyone has performed correctly, right? Beyond just obliging with their record-keeping obligations. Okay. The next thing is we want to actually make sure, has any one of them actually done something that they shouldn't? Have they performed some state transition? Have they sent a message that the correct implementation would not have done? So the way we do that in this particular system, as I mentioned earlier, is to use state machine replications. So again, here is where the assumption comes in that was just mentioned, that we assume that the actions of node can be modeled as a deterministic state machine. And again, if you have a piece of software that's not deterministic, you can typically, with a little bit of changing around the edges, make it deterministic by just recording things like random number generator seeds. Or when you take an external measurement, like you measure the temperature, and depending on that, your actions change, you record the temperature that you have taken. Okay? You stick it into the log. That means later on, based on that log, I can deterministically replay your execution. So what's happening is you take this log. So the state machine interacts with the network. It sends messages. It receives messages. We're going to stick that information into the log and some additional stuff, like these random number generator seeds, the temperature measurements and things like that. Or if we have, a multi-threaded execution, and then we'll record when we did the context switch. Okay, so when these witnesses now fetch my log and they want to do fault detection on it, they simply take a copy of that state machine, but not an arbitrary one. They take the one that they trust. They take the reference implementation. Okay, and they simply feed the inputs from that log that I've recorded into that state machine and see if the outputs that it produces match the outputs recorded in the log. Okay. So if all of those match, it means the state machine that I'm auditing has behaved exactly like the reference state machine. Things are okay. If not, then I know that there's been a deviation. And furthermore, I can now take the relevant piece of log that exhibits this deviation, okay, and turn that into the evidence that I was talking about. For instance, I can send that to other nodes and say, see for yourself. Right? Compare that execution to whatever state machine that you are trusting, and see for yourself whether you think this is correct or not. Okay, so so here is a bit of the summary of what this can actually do. If you put it all together, then it turns out that if a node commits a fault, meaning it performs a state transition that the reference implementation would not have done, and it has at least one correct witness, then the witness obtains either a proof of misbehavior or a challenge that the faulty node cannot answer. Right? This is again this thing where we cannot decide because the faulty node is actually not committed of a commission fault. It hasn't performed an action that's a smoking gun. It has simply refused to do some action, but we're not quite sure why. And the second property is that actually correct nodes cannot be accused. And this is true, interestingly, even if all of its witnesses are faulty. It's impossible for even a bad witness to generate a proof of misbehavior or produce a challenge that the good node could not immediately answer. Okay? So a bad witness could say, you didn't answer my message, right? And then someone else would say, well, hey, Peter, answer this message, and I would just acknowledge it. Okay, so again, remember the original motivation for this, I told you a little bit about the history, was actually to see if we can, for this, I'll take your question in a sec, whether we can have a more reasonable, less complex way of having a comprehensive way of dealing with misbehaviors in peer-to-peer systems. But of course, once you have a system like that, you try it out on other applications. Okay. Yes, I'll take your question. No, it just happens to be that this turns out to be the case. Remember there are these two properties. One is positive. It says, if there's a fault, I will detect it. That is contingent on having at least one correct witness. And of course, you want to make sure that your witness set is large enough so that, with very high probability, one of those witnesses will always be correct. But interestingly, as it turns out, right, for the second relevant condition, namely that good nodes cannot be accused, that condition is not necessary.
What we have heard is there is always a number f, the maximum bound of 40.
Right.
Is there something here also? Are you overlapping the witnesses?
No. So this is remember, first of all, this is not a fault tolerance technique, right? And therefore, it's also not based on consensus. Okay, and this is why it's not subject to the usual 2f plus 1 or 3f plus 1 fault limit, right? There's no contradiction here. So in fact, the way you stated here, it is not a fault bound, but simply this condition that at least one witness has to be correct. Okay, so it's a weaker condition. But of course, what you're getting in return is also weaker, right? It doesn't mask fault. It just detects faults. Okay, so back to these. So we've tried this out, of course, on a number of different systems. One is an NFS server in the Linux kernel, where you detect when that server is in fact faulty or buggy, right? It tampers with files, it loses updates, or it has incorrect access control, because you can replay its execution against another NFS server implementation you trust. We've applied it to peer-to-peer overlay multicast, where the things are typically not so latency sensitive, but you have big volumes of data. And there, obviously, you can do things like, you can detect automatically things like freeloading, right? Someone has modified their software to never provide any service, just use service. That'll cause a deviation, and you can trivially detect that it's not performing as desired. Similarly, if it tampers with content, okay, it'll just cause a deviation. And finally, here is this peer-to-peer email system that I mentioned earlier, where there's actually a huge number of different attacks against that, both against the content, against its availability, and against its DHT routing. And they're just sort of all captured in one package, right, by doing this kind of fault detection and then kicking out a node that has displayed a misbehavior. Also keep in mind, of course, that this is just one possible implementation of this concept of tamper-evident logging and fault detection, right? You could imagine different implementations of tamper-evident logging with different properties, and in fact, since then, different ones have been developed. And you can also imagine different fault detectors that are not based on state machine replication, right? Detection based on state machine replication has this big advantage that it's very general. You don't need to understand anything about the application. But it's also somewhat costly, right? You need to repeat every cycle of computation that you did during the audit. So anyway, let's talk a little bit about how much this costs. So in our experience with this particular system, of course, it depends very much on how heavily utilized your system is and what it does, right? How many messages it sends, what size of messages it sends. So among those applications I've just shown you, the log storage that you need to commit is between, or the amount of information that's being created for logging is about anywhere from 10 to 100 gigabyte per month. Keep in mind that this should not really be a storage problem, because you don't have to keep these logs forever, right? You just keep them long enough until they've been audited by all the witnesses. A more substantial cost is message signatures. Okay? That's a very fundamental inherent cost, because every message, every acknowledgement has to be signed, and that's non-trivial. If you use RSA 124 or so, which would now be not sufficient for really high security applications, it adds about 1.5 milliseconds RTT, which is not a big deal in a wide area system, but it could be a big deal in a local area network, latency sensitive application. It also obviously adds CPU overhead, although the nice thing is that can be very nicely overlapped, right? So multiple cores can help here. And the other cost is, of course, you need to periodically log transfer these logs to the witnesses through the network and perform the replay, okay? And that depends on a number of witnesses. Again, you want to make the number of witnesses large enough to make sure one of them is at least correct, but that, of course, also increases the overhead in terms of computation and bandwidth. One nice aspect is this can be completely asynchronous, right? So the witnesses can do their auditing whenever it's convenient. So if you have a system that has a diurnal load pattern, you would typically do the auditing during the night, right, when load is otherwise low. Let me just give you some more detailed performance evaluation here based on this peer-to-peer email system, where we're assuming that we have a certain set of dedicated witnesses that do nothing but witnesses, and you set them up in such a way that you're sure, right, at least one of them will be correct. So here is the baseline traffic of that's the per node traffic in this peer-to-peer email system before accountability was applied. When you're adding all the signatures and acknowledgements to the messages, right, which is the basis for the tamper-evident logging, you add something that's not very significant. But if you add the overhead for fetching logs, and sending them to the witnesses, the bandwidth overhead per node goes up quite a bit. In fact, you can't see that here, but it's quadratic in the number of witnesses. Okay. So for small numbers of witnesses, this is okay. If you want to have huge number of witnesses because you don't trust the individual witnesses very much, and you still want to make sure that at least one of them is correct, this could very well become a problem. So it turns out one thing that helps here. Let me just back off first. First of all, if in a really decentralized system, right, you wouldn't have dedicated witnesses. What you would want to do is you would want to, for every given node, want to have a set of randomly chosen other nodes that act as witnesses for this particular node. Okay. This is a little bit as if you did state machine replication and you're collecting replication sets from within a decentralized system. Now, of course, here you run into a similar problem, which is that no matter what witness number you choose, given a certain rate of expected faulty nodes, there's always a non-trivial probability that somewhere in the ring, for some node, right, you just happen to have a set of witnesses that you chose unluckily, such that all of them are faulty. Okay, so it turns out because of that, you cannot get a perfect guarantee, right, that everyone will have at least one correct witness. That's pretty fundamental, and that holds for any replicated system as well. But once you acknowledge this, right, that there is some probability that you might not detect failures of a given node, you might as well use that in the design of peer review and your tamper-evident logging. It turns out if you do that, actually you get the asymptotic complexity of this log exchange bandwidth down from order squared in the number of witnesses to log logarithmically in the number of witnesses, which helps quite a bit. So let me just show you here another view of the traffic overhead, the per node bandwidth overhead, which turns out to be the critical resource in this application. This is the email system before we applied accountability. Okay. Here is a typical DSL cable upstream. Actually, it's a little bit slow by now, right? It was a few years ago. If you use an assumption that up to 10% of the nodes can be faulty, and you have the number of nodes in the system here on the x-axis, you see that actually your overhead, because of that logging and because of the fact that you need a relatively large number of witnesses as the system grows to make sure that you have this guarantee or this high probability that you're going to have a correct witness everywhere, it quickly gets out of hand. In fact, at about a little over 100 nodes, we would exceed the upstream capacity of a DSL link. But if you apply this trick and you settle for a 6/9 probability of detecting a given violation, okay, in the way you exchange messages among the witnesses, you get back to, like I said, a log n, and now it fits nicely into the bandwidth budget, even up to about 10,000 nodes. Okay, so at this point, let's take a step back. I want to focus a little bit on the limitations of that system and alternative designs that have been done later for different applications. So first of all, I mentioned state machine replication is nice because it's very general, but it has its costs. An alternative, of course, you can do is if you do have a specification of a system, even if it's a partial one, right, including the properties that you most care about, you can do a sort of a handcrafted, an application-specific fault detector. And if you do that, you can reduce that cost of auditing dramatically, and that's been done in a number of applications. Another issue that I haven't disclosed yet is that the logs that you capture for state machine replay, they're very verbose. They actually include much more information than you strictly need to verify whether a node has in fact done the right thing, because they include all this low-level information that will allows you to do full replay. Okay, like in particular, they include the seeds of your random number generator, which can be particularly unfortunate because once a node has audited you once and seen your random number generator seed, it can actually predict your future actions. Okay, it can predict your future choices. And that's really bad if you, for instance, are thinking about a game, where that makes the actions of another player completely predictable in the future. So it turns out you can do some crypto techniques. There's a way of generating random numbers in such a way that you can audit whether a path, the prefix of a sequence up to a certain point is correct, meaning it follows, in fact, it's a pseudorandom, it's a correct pseudorandom sequence, but it doesn't reveal anything about it, future choices that you're making. So that helps. The other thing in general that helps is if you have a specification-based fault detector, same thing as here, is not only going to be much faster, but it requires, in general, far less information. Thereby, you're leaking much less information, and your loss of privacy is much more controlled. I said that there is some application engineering you need to do. It's not very substantial, but you have to, to apply the peer review library, you have to have access to the source code. You need to understand where that software is making non-deterministic choices. You need to extract the sources of that non-determinism. So there's some things you need to do. It's non-trivial. There's also a way of doing that at the level of a virtual machine, which means you can apply it to any arbitrary system image. The other important thing, which I haven't talked about yet, this technique only accounts for integrity of a computation, meaning it verifies that the computation has done all the right things it's expected to do. It doesn't say anything about whether or not a node has done some additional things that it wasn't supposed to do, which means we can't say anything about information flow, and that means we can't say anything about confidentiality. Okay? So suppose you have a system here, and there's a malicious node in it that does all the right things, but it also, takes a copy of all the information it sees and sends it through another channel to some node, leaking essentially all the information to the outside. That's not something that this technique could deal with. Okay? So it only covers integrity, not confidentiality. It turns out that, and I'll talk to that in a minute, a little bit, if you have this virtual machine-based approach to accountability and you trust the virtual machine monitor, you can account for information flow. This requires a public key infrastructure because individual nodes need to be able to sign keys. And in particular, right, you need to really make sure that you can identify nodes by their public key, because otherwise people could misbehave, right, and then say, it wasn't me, I don't know who that was, right? Here's my public key. So Sybil attacks are still a problem here. If you can't have a public key infrastructure, there are also approaches based on web of trust, and that's been explored. The other issue is, you may have noticed that during an audit, I have to verify a lot of signatures. Right? There's lots of messages recorded in a log, and I need to verify them all, which turns out that's not such a big deal in a peer-to-peer situation where everyone is a witness for someone else, and you do that at your own leisure, and the total number of nodes that you're a witness for is not so large. If you want to do auditing in a centralized manner in a data center, that would become a serious issue. But it turns out you can actually redesign these tamper-evident logs to make sure there's not a signature on every message, but there's only one signature that you need to verify for each node that your audited node has communicated with. Okay? So that's much, much better. So the other more serious limitation is that, if you think about it, to be able to replay an execution of a node, I need to not only have a record of its actions, but I need to also have access to its state. Okay? This is not a big deal for many applications that don't have substantial state, but if there's a database behind it, right, how do I get access to that database? So you can play all kinds of tricks. You noticed we had done this for an NFS file server, which of course has lots of state, but you can help yourself by working with Merkle hash trees to see whether the state that I have is equivalent to the state of the audited node. And if it differs, I just get the differences, right? So you can make this quite efficient, but nevertheless, it can quickly become a problem in sort of big data-like applications. One thing that could help is if you have a versioning database, right? If you could sort of, during replay, refer to previous versions of the database at the time when the log was recorded. Okay, let me cut these things a little bit short. I was going to show you a little bit here or give you just a flavor of other applications that this has been applied to. This is a system that applies accountability for interdomain routing, basically BGP in the internet. where the issue is, you have different ASs, autonomous systems, or you can think of them as ISPs, cooperating with each other, and they would like to actually be able to hold their peering partners accountable for their actions. But the situation is here a little bit different. First of all, you really don't want to have a global PKI, right? Nobody is willing to, or at least it's a very hard sell. So instead, you want to rely on a web of trust, leveraging the peering agreements that already exist between the ISPs, and that can be done. You also want to limit the auditing to the peering partners, but that turns out to be okay. As long as everyone is audited by someone, things still work. And you also want to deal here with accountability zones, because you have to expect that there's only a partial deployment, right? You can't expect every ISP in the world to adopt this technique like on day one. By the way, this particular thing also doesn't use state machine replication. That would be unreasonable. Okay? You couldn't possibly do state machine replication on the entire internet backbone traffic. So instead, what's happening here is that there's a customized fault detector that basically just says, did this thing perform, first of all, according to the BGP specification, which is fairly simple, and did it, in fact, behave according to the peering agreements that exist? So these are the business contracts that exist between the ISPs. This is a more recent system. What's happening is that in commercial content distribution networks like Akamai, there's recently been a trend towards including some peer-to-peer aspects. Okay, so for some types of contents, you actually, as a client, get to download a piece of software which is capable of exchanging information with other peers. Right? So there's some swarming aspect to it, but it introduces a bunch of problems, because it includes the possibility that someone might corrupt that software and then do various malicious things along the lines of what we discussed. So we designed a system here that basically uses tamper-evident logging to allow the control plane and the Akamai data center infrastructure to periodically check the actions of those peers to make sure they haven't been compromised. And again, the trade-offs are a little bit different, right? You want to design the tamper-evident logs differently here, because you want to optimize them for efficient auditing in the data center, and you also want to you don't want to use state machine replay, right? We want to use basically a fault detector that has been handcrafted to check for correct execution relative to a state machine that has to hold for a correct client implementation. And here finally are these accountable virtual machines that I mentioned earlier. So here the idea is, in peer review, right, to make something accountable, you have to take the application and link in the accountability library and make various modifications to make that work. Here, you actually apply the accountability techniques, so maintaining tamper-evident logs and state machine replay, you integrate that into an accountable virtual machine monitor. So what we did in particular is we took the VMware Workstation software and added the capability of doing accountability, which means you can now run conventional VMs, but you can also run other completely unmodified system images and mark them as accountable, which means that the system during the execution keeps a tamper-evident record, which can then be taken and run on another instance of the accountable virtual machine against a reference copy of that virtual machine that you want to audit. And again, so you can do that for complete shrink wrap software. So we've done it actually for we stuck in Linux into one of those things, or Windows actually, stuck in Windows in one of those machines and ran Counter-Strike on it, which is a shrink wrap commercial multiplayer game. And then you play with someone, you record the log, and then you can ask them to give you the log, and you can verify whether they've been cheating, right? Because cheating is very prevalent in these games. You guys probably know that better than I. There's sort of thousands of cheats that you can download on the web, and they're basically patches that change the Counter-Strike image, right, to give you unlimited ammunition or whatever they do. Okay, so the other interesting thing is you may have noticed that, in fact, peer review doesn't rely on any trusted components on the node that you're auditing, right? Which is very nice. if you're willing to give that up and assume that the accountable virtual machine monitor implementation that's running on the node that you want to audit is trusted, then you can use that to also account for information flow. Right? So if you think about it, if that node were to try to leak information, so it wants to open another communication channel and leak private information to a node outside of the system, the VMM, of course, would notice this and record that. Okay, so let me wrap up. We're just on the hour anyway. So this accountability concept basically focuses not on fault masking, but on fault detection, but it tries to do it reliably. And also it tries to identify a faulty node associated with that deviation. And it tries to produce evidence that you can take then to convince third parties that a fault has happened and who's responsible, who's sort of causally responsible for it. I shouldn't say who, which component, because there's another mapping to a person which is not necessarily easy. It's, it seems practical, at least for an interesting set of applications, but we certainly don't understand fully yet how large that scope of applications is. And you have some design alternatives and trade-offs, right? The state machine replay technique is very general, but it's costly. If you're willing to have a customized fault detector for a specific application, you can do much better in terms of audit performance, and you can also increase privacy because you're not leaking as much, additional information. You can pretty much design that to get close to the minimum information necessary to allow the auditor to verify whether you've complied with whatever the specification is. And if you're willing to have trusted components, like willing to trust that accountable virtual machine monitor on the node that you want to audit, you can also get information accountability. I'll leave you with that. Thanks a lot for your attention, and if you have any more questions, go right ahead. Yes?
So witnesses can fail, so it doesn't make sense to apply peer review next to failures, and if so, is there a fixed point?
I'm not sure there is a fixed point, unless you believe that at some point you can afford such a large witness set or such controlled witness set that there's definitely going to be one correct. But I'm not sure it's worth it, right? Because the failure condition is pretty clear. You need to arrange for at least one of the witnesses to be correct. The problem, of course, is that the main cost you have is that if in fact that's not true and you're unlucky enough that all of your witnesses are faulty, you won't know. Right? So the accountability does in fact not hold with respect to the property that at least one of the witnesses is correct. But I think that's a sensible way of saying, let's stop here, and that's what we did. Right? We just built in this assumption that one witness is correct and stopped at that point. One reason we did that also in the context of peer review, at least, is that since the state machine replay is so expensive, you don't want to do it several rounds. There was another question, I think, somewhere. Yes? Yes. So it turns out actually there's a lucky coincidence almost that modern virtual machine monitors already have the capability of recording and replaying an execution. Okay. So first of all, let me actually take a step back. So it may seem surprising that you can take an arbitrary piece of software that clearly has non-deterministic choices in it, right? Like spread scheduling, random number generator seats, and so forth, that you can record such an execution and replay it deterministically without cooperation from that image. The reason is that the virtual machine monitor has basically control and visibility in all the low-level events, right? It knows exactly what's happening. So that's why you can do that. Subject to multi-cores, right? It actually turns out when you have multi-cores, things get really difficult, and that's an open problem. So in fact, this will only work, I'm sorry, I should have mentioned this. This will only work on a single core per VM. You can run this on a multi-core machine, but if you want to make it accountable, you can only assign at most one core to a given VM. So these machines already have, these systems already have that capability. So it was relatively easy to add the accountability technique. We just had to add support for tamper-evident logging and a few other things. Sorry? Yeah. Yeah, definitely. I mean, there's much more detail in that paper. Mm-hmm.
So I believe that in order to really have this kind of accountable AML, so you have to have some plugin that has to work at the hypervisor level at the same time. You have to have something at the application level as well. Don't you? I mean, you're saying that.
No. So the first part, you're quite right. You have to go into the virtual machine monitor. So we had a source code license from VMware to do this, right? You cannot do that without the source code, I believe. It would be pretty hard. On the second part, the answer is no. You don't need any application cooperation. But perhaps we can take it offline to discuss this in more detail, okay? Are there more questions? Yes? Sorry? Well, I would call it weak synchrony, okay? Because all you really assume is that good nodes can eventually communicate. So if there is a network failure, right, it'll eventually get fixed. Any other questions? All right, well, thanks for your attention through these 4 or 5 hours, and hope you enjoy the rest of the summer school and enjoy your lunch. You've been a fantastic audience, by the way, right? Very, very good questions and lots of questions. Perfect.